the molecular mistake that nearly ended an industry. It was invisible, cheap, and once released, impossible to take back. A single molecular decision nearly erased an entire industry from existence. At the time, it looked like progress. A chemical solution to a physical problem. Stronger, lighter, more efficient. The kind of breakthrough industries wait decades for. But chemistry does not care about intention. To understand why this matters today, we need to revisit how materials earn trust. Industries rely on consistency, repeatability, predictable behavior under stress. When chemistry behaves, systems scale. When it does not, failure multiplies faster than warning. The first narrative beat begins with substitution. A new molecule replaces an old one. It performs the same job, but cheaper, easier to manufacture, more flexible. On paper, it is superior. Testing confirms short-term success. The market embraces it immediately. The speed of adoption was itself a warning sign. In retrospect, the second beat arrives slowly. The molecule behaves differently under real conditions. Heat alters its structure. Stress changes its alignment. Exposure triggers reactions that were never considered. But these changes happen at scales too small to see, too slow to raise alarms. The gap between laboratory conditions and field conditions is often where molecular failures hide. At first, defect appear random. A failure here, a recall there. Engineers blame manufacturing. Users blame misuse. No one blames chemistry. The molecule still passes standard tests. The industry keeps moving. The attribution problem is one of the most dangerous aspects of molecular failure. The third beat forms quietly. As products age, patterns emerge. Failures cluster. Timelines shorten. Margins disappear. The same molecule appears at the center every time. The problem is no longer isolated. It is systemic. This is where tension begins. Because the industry has already committed. Factories are built. Supply chains locked. Standards written. Reversing course is expensive. Ignoring chemistry is cheaper. For now, the economics of commitment create a powerful incentive to explain failures as exceptions rather than as symptoms. Exceptions can be managed locally, but chemistry never negotiates discounts. It compounds mistakes. And once a molecular flaw enters mass production, it does not fail once. It fails everywhere. The distribution of a flawed molecule through a production ecosystem is not a linear process. The mistake was not choosing a bad molecule. It was trusting short-term performance over long-term chemistry. And that error would push an entire industry to the edge of collapse. As products spread into the world, the molecule faced reality, not controlled labs. This is where chemistry revealed the flaw. The molecule contained a weak bond, stable enough at first, but vulnerable under repeated stress. Each cycle stretched it. Each exposure nudged it closer to failure. Degradation was slow, then sudden. The slow phase is the dangerous phase. It is when the appearance of reliability is maintained while structural integrity is being consumed. At first, the damage hit internally. Microscopic cracks, subtle chemical rearrangements. Properties drifted out of specification. The material still looked intact, but strength was quietly leaking away. The invisibility of early-stage degradation is a feature of many molecular failure modes. Failures began appearing years after production, not days, not months. This delayed timing masked the cause. Warranty periods expired. Records disappeared. The molecule kept aging in silence. The multi-year delay between production and failure is one of the most consequential aspects of long-term molecular degradation. It disconnects cause from effect in ways that protect the original decision from accountability. The industry reacted defensively. Patches replaced redesigns. Inspection schedules increased. Blame shifted between suppliers. But chemistry remained unchanged. The same molecule kept reacting. The same bonds kept breaking. Defensive reactions are often rational from the perspective of individual organizations managing their immediate exposure. Here is where the conflict sharpened. Replacing the molecule meant admitting error, rewriting standards, recalling products at massive scale, billions in losses, legal exposure, reputation damage. Ignoring it meant accepting escalating failure. The decision calculus was genuinely difficult. Neither option was without severe cost. The difference was that one cost was concentrated and visible in the short term, while the other was diffuse and grew over time. What nobody expected was cascade. One failure triggered another. Systems designed with redundancy failed together. The molecule was everywhere, in critical components, in load-bearing structures, in safety systems. A single chemistry choice linked them all. The assumption behind redundancy is that individual failures are statistically independent. When multiple components contain the same flawed molecule, and that molecule degrades through the same pathway under the same environmental conditions, the independence assumption fails. Failures become correlated. The tipping point arrived quietly. A high-profile failure, public attention. Regulators intervened. Testing expanded beyond short-term metrics. Long-term chemistry finally entered the conversation. The regulatory response that followed was not technically sophisticated. It did not require understanding of a specific molecular mechanism. It required only that testing protocols include longer timescales and wider environmental ranges. And once it did, the conclusion was unavoidable. The molecule was unsuitable for the role, not because it was weak, but because its chemistry aged poorly. Time exposed what early success had hidden. The industry now faced an impossible choice: undo years of progress, or accept that chemistry had already decided the outcome. The crisis forced the industry to confront its assumptions. Performance was no longer enough. Investigations revealed the pattern clearly. The molecule degraded through a specific pathway. Heat accelerated it. Stress guided it. Environmental exposure completed it. The failure was not random. It was predictable once chemistry was understood. The predictability was deeply uncomfortable for the industry. It meant the failures were not bad luck. This realization arrived too late. Millions of products were already deployed. Replacement was slow, expensive, disruptive. Supply chains fractured. Confidence collapsed. Here is where tension peaked. Because the molecule had been optimized for manufacturing, not for longevity. It met every short-term requirement, passed every early test. But long-term reaction pathways were ignored. The industry had tested function, not fate. The distinction is fundamental. Function describes what material does under controlled conditions in a narrow time window. Fate describes what it does under real conditions across its full service life. Engineers face a new problem. Chemistry operates on timescales markets do not. Years, decades, lifetimes. Design cycles rarely accommodate that. Yet chemistry never accelerates to match deadlines. It waits. The mismatch between commercial timescales and chemical timescales is structural. It does not resolve itself through better intentions. The response required humility. Redesigns prioritized stability over cost. Testing protocols expanded. Accelerated aging became mandatory. Margins were restored not through strength, but through understanding molecular behavior over time. Accelerated aging tests, exposing materials to elevated temperatures, stress cycles, and environmental conditions designed to compress years of degradation into weeks of laboratory time, became standard practice. The industry survived, but only after retreat. Products were simplified, performance targets lowered, costs increased, growth slowed. Chemistry imposed limits where ambition had ignored them. This is the core lesson. Progress that ignores chemistry eventually collapses, not dramatically, but comprehensively. Every shortcut compounds. Every ignored pathway waits its turn. The molecular mistake did not destroy the industry. It reshaped it, forced it to respect time, to value patience, to acknowledge that materials live lives of their own. And that leads directly to the final reflection. Because this story is not isolated. It repeats whenever speed outruns understanding. The climax is not the failure. It is the correction. The industry survived because it finally listened to chemistry, not market pressure, not timelines, not optimism, Chemistry revealed what time would eventually expose anyway. The resolution is sobering. Innovation cannot ignore molecular behavior. Short-term success hides long-term risk. Performance without durability is a gamble. And chemistry always collects its debt. Modern relevance makes this lesson unavoidable. Faster development cycles, new materials, rapid scaling. The same pressures exist everywhere. The same mistake waits to repeat. This reframes responsibility. Design is not just about function. It is about future behavior. How molecules age, how bonds respond, how reactions unfold over time. Ignoring this is not ignorance. Once you see this, progress feels different. Not slower, but more deliberate, less flashy, more resilient. Chemistry does not punish innovation. It punishes haste. The molecular mistake that nearly ended an industry is no longer a warning from the past. It is an instruction for the future. Understand reactions fully. Test beyond excitement. Because chemistry never forgets. It never forgives shortcuts. And it never stops reacting. Subscribe to join the journey. The molecular